Okay, so let's talk about the two-step process, which is going from benzaldehyde to benzoin, and then next week we are going to go from benzoin to benzyl. So let's write down the overall sequence. We have two benzaldehydes, which are going to combine together, so it's kind of like a dimerization reaction. So this week you're going to set up the secondary alcohol. You're going to set up this first part, this is part A, and then we are going to oxidize the secondary alcohol into a ketone so that it gives you benzyl. This is part B. All right, so the way the reaction will proceed, and just a couple things about it. First things first, what kind of an aldehyde will go through benzoin condensation reaction? The kind of aldehyde which does not contain an alpha proton or an alpha hydrogen. When I use the word alpha hydrogen, what I mean by that is, let's say you have an aldehyde. So this is your functionality. That's your functionality. The first carbon that you hit, that's called alpha. The next one will be called as beta. The third one will be called as gamma, delta, so on and so forth. So if you don't have any hydrogens present over here, you're going to say that it will go through the benzoin condensation. So for instance, what I have over here will not. And notice what you have in your experiment is benzaldehyde. So obviously there is no hydrogens over here at this particular carbon, because carbon is supposed to make only 4 bonds, and since it's a benzene ring, 3 of those bonds are a part of the ring and 1 is coming out to the ipso functionality, and so you would say that this sets up the stage to go through a benzoin condensation reaction. Realize 2 moles of the aldehyde are going to be dimerized, so in terms of yield you'll have to keep that stoichiometry in mind. Now, you might ask, why is it that we are using thiamine? What is that? That's vitamin B1 that we are going to use. And really, this is not the only reagent that could be used. You could use something like sodium cyanide. So you could use a source of cyanide for this purpose. Recall from class, it's going to add in a nucleophilic fashion. The Cn negative is going to attack, and you will get a negative on oxygen. You have Cn, and of course, since it's going to be done in aqueous solution, so you can have OH and a Cn, so a cyanohydrin is generated, and then that, when treated with the base, essentially gets rid of this benzylic hydrogen, which brings you OH, Cn, negative charge, and that negative charge will then attack another species. So that negative charge attacks right here. So mechanistically they are very similar, but hopefully you can see, we discussed that in class as well, that we do not use cyanide when we can avoid that. And the reason for that is because cyanide is going to form a stable complex with your hemoglobin, and since that's going to deplete the ability of hemoglobin to transport oxygen, which ultimately is fatal, so due to the toxic nature of the cyanide, we prefer not to use this this particular reagent. Mechanistically, it's the same thing. So there will be an exchange of the proton and exchange of protons. So you will say that the negative charge, I'm going to show over here, maybe make some room. pH. Let's write that as pH so we can follow along the arrows. And an OH. So that's a proton transfer. And that gives you another pH. Negative charge comes back, C and leaves, and that's your benzoin. Now, mechanistically, it's exactly the same thing what you will get using the thiamine as well. So let's just see how that one will look, or what that one will look like. Like I said, you're going to begin with thiamine hydrochloride salt, and you're going to essentially take only about 0.7 grams of that, and you will dissolve that in water. You should see that most of it with the 1.5 milliliters water should dissolve, most of it. And if there is some, flakes here and there that do not, that's okay. They will eventually dissolve. But try to get as much in. Now, realize the purpose A of using essentially a hydrochloride salt is because that would be soluble in water, and so the reaction can work really well. Now, when you add the base to the system, essentially you're going to get rid of the HCl. That's one thing for of course, and the other that's going to happen is you're going to get rid of this acidic proton. So hopefully you can see that that hydrogen, which is right next to a positively charged nitrogen, is going to be fairly acidic, and that's the hydrogen that will be lost first. So the OH negative is going to simply pick up this proton, and now your electrons are going to sit right here, and that is what is going to attack on the benzaldehyde. Now, procedure wise, like I said, you were going to begin with your 0.7 grams of thiamine hydrochloride, and you're going to first dissolve that in water, and then you're going to add 8 milliliters of ethanol. And like the procedure says, that you should stir it till it's homogeneous. So basically you will see when you add the alcohol, essentially the clear solution is going to become milky, so there'll be cloudiness, and that's okay as long as you don't have many lumps. Okay, so just let it be a homogeneous slurry type of a consistency. And at that point of time, you're going to add the sodium hydroxide. Again, the reason why you're adding sodium hydroxide is basically because you want to get rid of the HCl, and you want to get rid of the most acidic hydrogen, like I was talking about earlier. And so you are going to see a big change in color. It's going to go from the white slurry like consistency to a very, very bright, very stark, very yellow, golden yellow color is what you're going to see. It's a very bright color that you will see. And so that will be the generation of this negatively charged nucleophilic situation, nucleophilic carbon, which is going to be used with the 4 milliliters of the benzaldehyde. You will see as you add the sodium hydroxide that yellow color, which gets generated only for a split second. I mean, it doesn't last for a very long time, but it tells you that the active species has been generated, and that color will fade out, a little bit. And of course, that color is because of the conjugation that is set up now in the system. As long as your solution looks like a faint yellow color, it'll be fine. And at that point of time, you're going to add benzaldehyde, 4 milliliters of that, and so your active species, which is the nucleophile right here, is going to attack, causing the negative charge to go on top of oxygen. Of course, that's going to exchange a proton to basically give you the alcohol, and in presence of the base, you're going to remove the uh, most acidic proton, which is going to generate a negative charge. That negative charge is in conjugation with the positive nitrogen, so that's why we have that generation of that very uh, uh, generation of that yellow color, which kind of remains. At this point of time, essentially, you're going to show. So here's the resonance. At this point of time, you're going to show how this negatively charged benzylic position is going to attack another molecule to carry out that dimerization reaction. Proton transfer, of course, will occur from one to another, and that will cause the loss of that thiamine. So thiamine, hopefully you can see, is going to act as a catalyst. It's only going to be used up in one stage and going to be regenerated in another stage, and your product, your final product, is going to get thrown off in a week's time from the solution. It does take time to precipitate out, but this process really is the best out of all. It's difficult to go wrong here, but in the past I have seen, if you added the sodium hydroxide, for instance, if you added that too quickly, and the color, the final solution that you have, sort of starts looking like a caramelized sugar brown, there's a problem. As long as you see a golden brown, you should be fine. Now, hopefully you can see that in both the cases, the cyanide example that I gave you, and of course the thiamine hydrochloride that we have, these are, mild bases that I'm using. So these are groups that are nucleophilic in nature. They are mildly basic in nature. They have the capacity to carry out the attack at the electrophilic carbon, but then when their job is done, essentially they will be lost from the system. So that bond between the carbon and the nucleophile, that must be broken. If that bond is too tight, essentially the reaction is not going to make it. Okay. Now, so tomorrow, for Wednesday's class, what you will do is you're basically going to put everything together, mix it, swirl it well, label it, and leave it on the tray. And then through the week, it's going to crystallize, crash out. When you come in next week, you're going to filter the material. You're going to then take the steps necessary past this point of time. So when you come in next week, you don't have to actually do this step, place an ice water bath for crystallization. 1 week is ample amount of time to get your solid product. If you don't get it in 1 week, there's no way you don't have it there. It's as simple as that. So the little hint that I gave you, your color at the time of mix should have a hint of golden yellow, but it should not be like a caramelized brown type of color. It shouldn't be that. But at that point of time, when you come in next week, what we will do is we will simply, since it would be ready, it would have crystallized, we would simply go ahead and vacuum our system. We will wash it with cold ethanol, and we will set it for drying for about 30 minutes, and we'll take the melting point. So during that 30-minute period, we are going to, go over the next chapter, carboxylic acid, wherever we would have stopped. We are going to continue our discussion there. So after everybody has set up, we are going to continue our discussion, and then we'll do the same oxidation reaction that we ran actually last week, which was based on aldaric acid. Now, I did say in class, I told you that these are two different experiments. That means you are going to be writing two different aims. One which will say that you have the synthesis of benzoin. So to synthesize benzoin. And so you have the materials required, you have the procedure, you have the observations, and in your final conclusion, I am seeking the IR analysis between benzaldehyde and benzoin, which you guys are going to take next week. you're going to be figuring out the melting point of benzoin that you found. You will determine the percentage yield. So those are the three things you'll discuss there. And of course, the post-lab questions for part A are 1, 2, 6, and 7. And then you will run the second half of this, which we are going to follow the book for, and that's simply an HNO3 oxidation. We do not use again the KMNO4 and the periodic acid, because periodic acid A is going to cleave that molecule. Even though it's a great oxidizing agent, it can cleave pH. It can cleave right here. KMNO4, that's a pretty strong oxidizing agent as well. Plus the MnO2 that gets generated gives you, or will give you, a hard time to purify the product from. Chromate, of course, is a problem because it's toxic. We don't want to use that. And we have seen we get very low yields in those oxidizing agents, so we are not going to use that. So HNO3 works just fine, and we are going to utilize that to carry out our nitration much the same way as we did. So our expectation will also be the same. We will expect the red brown color that will be generated, so all of that will still hold true. So next week you're going to follow the student notes for that particular week, and we'll take it from there. It will be something that we will run in the hood. For this week's lab, we will stop at essentially this stage on Wednesday. All right, see you in class.